2.6 starts our study of combinations and composite functions. If you've taken AP Pre-Cal, the composite functions part should look familiar. The combinations of functions is a little bit different than probably something you've done in another class, but that's okay. Before we really get into combinations and composite functions, let's take a second and talk about the domains of functions. So all functions have a domain of all real numbers. So if we look at this, okay, again, most functions have a domain of all real numbers except for the following 4 problems. Number 1, functions that model verbal or real-life conditions are going to have restrictions to the domain. Because if you're talking about selling shoes, yes, yeah. If the problem is talking about selling shoes, you can't have or sell a negative number of shoes. So there are some restrictions on the domain when the things are representing real stuff in real life. The second type of restriction on a domain we have is for our rational functions. We talked about this in chapter 1, that if there's something in the denominator that's an x, that denominator is not allowed to be equal to 0 because it would make the function undefined. So when we're dealing with restricting domains, you just have to make sure you throw away any numbers that are in the denominator of that function. The second type of function, third situation, where you would have a domain that's not all real numbers is for a square root or an even root function. And basically, the radicand, which is the fancy word for the stuff underneath the square root, must be greater than or equal to 0. And this makes sense to us because in the real number plane, you can't take the square root of a negative number. So we restrict our domains to only being input values that are positive. The last type is a logarithmic function, and we're not even discussing the logarithmic functions till chapter 4, but just so that it's on this list, there are 3 function types that do not have all real numbers as their domains. It's rational, square root, and logarithms. We're going to be focusing on the first 2 today, as well as some potential real-world situations. So let's answer just questions simply about domains. We find the domain of the first function. They're green. Yeah. First question we ask ourselves is, what function type is this? So what function type is this function? Because it has this little square right there, what kind of function is it? Starts with a Q. It's a quadratic. Quadratic functions are not on my list of values or functions that have a restriction on their domain, which means that we can automatically answer that the domain is from negative infinity to infinity. And I'm going to be asking you today to have your domains written in interval notation. So make sure we're practicing interval notation. How about letter B? What kind of function is letter B? It's a good cue, right? Is it what? It is a fraction, so we call it a rational function. A rational function has the restriction that the denominator cannot be equal to 0. So we're just going to snag the denominator, leaving the numerator alone for this chapter. And we're going to say, hey, that denominator, x squared minus 2x minus 3, cannot be equal to 0. And whatever's down there, we have to solve. Now, the function type that you're solving here can change. This is a quadratic instead of a linear function. So to solve quadratics, we would factor. We ask ourselves, what are the values that would multiply to 3 and add to negative 2? Where those values would be negative 3 and positive 1, because negative 3 times 1 is negative 3, and negative 3 plus 1 is negative 2. Which also then means that each of these individual factors will give me one of the restriction values. Bless you. We would say x is not allowed to be equal to 3, and x is not allowed to be equal to negative 1. Do we see how I got those numbers? We just changed the sign. Now that is a way to display the domain because it's all real numbers except 3 and except negative 1, but I want my answers written in interval notation, which would mean that we are answering that this is fine from negative infinity all the way to negative 1, then we take a break. Then we go from negative 1 to 3, then we take a break. Then we go from 3 to infinity. That is basically the entire number line with gaps at negative 1 and gap at 3. That's what this interval notation is saying. We can use the section before -1, or the section between -1 and 3, or the section after 3.
That's what the union?
That's what it's the word or. It's the union symbol. What kind of function is letter C? Square root. It's an even root function, specifically a square root function. And we know that the radicand, the stuff underneath the square root, is not allowed to be negative. And we know that. That's just a property of even roots. So what we will do is we will take the stuff underneath the square root and set it greater than or equal to 0 and solve for x. Again, whatever type of function shows up there, if it's quadratic, you factor and solve. If it's linear like this one, we just solve. So we would subtract 12 from both sides. We get 3x greater than or equal to -12. We divide by 3 on both sides. Do I need to flip the sign?
Yeah.
Are you sure?
No, you didn't divide it.
I didn't divide by a negative. That's the only time that you flip the sign. So we have x greater than or equal to -4. And if we're writing interval notation for this, numbers that are bigger than -4 are -4 off to infinity. So we would answer that the interval for the domain is from -4 to infinity. Why did I use the bracket instead of a parenthesis?
Because of the closed.
Tell me more.
It's closed.
What's closed? The or equal to symbol would be closed. Yes. Correct. Correct. Because it's closed.
Yeah, it's closed.
She's asking why it's closed.
Okay, so question on this last one. What kind of function is it? What kind of function is this last one?
Cube
Quadratic.
root. I just spit something out.
It is a rational function.
And what you're so freaking smart.
Is it only a rational function?
Square root.
There's also a square root in it. Rational with square root. So we have two problems that we need to solve. We know that this stuff in the denominator is not allowed to be equal to 0. We also know that the stuff underneath the square root cannot be negative. So instead of solving two separate things, what we're going to do is combine those two rules and say that the radicand, the stuff underneath the square root, can only be greater than 0. Weird question, right? Because here I use the greater than or equal to, and now I just use greater than. Why would I do that?
Because it can't. No.
Because where is this square root? On the bottom. And can the bottom be equal to 0? So why would I put that little symbol right there, right? We just remove it. Because now we can only be greater, not equal to 0, since it's in the denominator. We solve for x, however, it asks us to. This is a linear function, so we're going to do -2 greater than -14. What do I divide by this time? A negative, which means that I will flip my sign, and this becomes x less than 7. To be less than 7 means that we are on the left side of the number line, which means we will have an interval from -infinity to 7. So in questions that ask you to find the domain, if it's a quadratic or a cubic or a linear function, easy answer, it's all real numbers. It's only for rational functions, square root functions, and eventually logarithmic functions that you have to do anything weird. What's up?
Why is the square root, why is that closed?
Why is the square root closed for here?
Yeah.
Can you take the square root of 0?
No.
You can. What's the square root of 0?
0.
0. So since we can actually do that, it can be equal to 0. It just can't be negative. So it just has to be greater than or equal to 0. Yes?
So you're not worried about like anything on top?
Nope. Numerators won't make any sort of weird things happen. Unless the numerator is like a square root or a logarithm, then we deal with it. But if the numerator is any sort of polynomial, polynomials' domain is all real numbers. We can start to talk about how we combine different functions together. So we're about to do arithmetic, adding, subtracting, multiplying, dividing with functions. Don't overthink a lot of this stuff. The weirdest part is the notation. If you see this, that means we are adding the function f to the function g, which mainly means all you have to do is combine like terms. CLT, combine like terms. To do the difference of them, make sure you do this in the order it says. So we'll take the f function and subtract the g function. All you have to do for this is distribute the -1 and then combine like terms. This is important on notation for the product. If you see f and g smushed next to each other with nothing in between them, we won't be using the little dot to talk about f times g because it'll be confusing later. Just f and g put together. You are multiplying f times multiplying g, which means for the most part you're going to have to FOIL or double distribute, doing all of the arrows business to multiply the functions together. The last one, to find the quotient, which is just f divided by g, you will have to divide and then deal with the fact that you now have a denominator and you have to find the restrictions. So you do some division and then you do the restrictions, because you are creating a problem by putting a function in the denominator. Okay, the one other thing we're going to highlight in this little section before we flip it over is that the domains for the combinations of these functions are the set of all real numbers common to the domains of both f and g. So if there's a restriction in f or g, that restriction is continued in the combination, which you won't see that often happening. So let's see what it looks like to do these sorts of things. On the back side, here's all of the practice problems. It says that we're going to let f be equal to 2x minus 1 and g be equal to x squared plus 2x minus 2. So I'm going to highlight today, I'm going to do f of x in red and g of x in blue. Yeah, you get it. It's a shade of red. It's pink. So the first question here wants me to find the sum of these two functions. So I'm going to add together f and g. The notation is important here that you get it correct. So we are writing that f plus g, in parentheses, of x will be equal to the f function, 2x minus 1, added to the g function, which is x squared plus x minus 2. I am just adding the two functions together. Make sense? We combine like terms. We'll start with the largest exponent, which means our final answer here will be x squared plus 3x minus 3. That's just combining like terms together. Oh, I forgot to do something very important. Before we started this question, we should have looked at the f function and the g function and talked about their domain. What kind of function is f? Starts with an L.
Linear.
What kind of function is g? Quadratic. Do either of those have restrictions? No. So the domain of f is from -infinity to infinity, and the domain of g is from -infinity to infinity, which means that the combination will be the combination of those two domains, which means that the domain of this function is still from -infinity to infinity, because we took an all real numbers plus an all real numbers and made another quadratic, which is all real numbers. This feels silly until it's a problem. I promise you, just keep following me. If we're doing the difference between these two functions, again, in the correct order, we would be doing f minus g of x, which means we take the f function, 2x minus 1, and we're going to subtract the entire g function. And we're going to make sure we put the entire g function in parentheses so we remember that we're subtracting the whole thing. You will make sure to distribute this negative to all parts of the g function. If that's 2, 3, or 5, you will multiply it to all parts, which means that we have 2x minus 1 minus x squared minus x plus 2. Once we distribute, we combine like terms, putting it in standard form, which would be negative x squared plus 1x plus 1. For this one, we took an all real numbers plus or minus an all real numbers and made a quadratic, which means that the domain is still all real numbers from -infinity to infinity. When we are doing the product, notice that f and g are smushed next to each other. That means that we are multiplying. What we are going to do f times g of x is we are going to take those two functions and smush them next to each other. So we're doing 2x minus 1 multiplied by x squared plus x minus 2. Notice that they are smushed next to each other, and to keep it from looking like just a jumble mess, I'm going to put them both in parentheses. Hopefully your brain is looking at this and saying, this is just a double distribution. I'm going to have to do this and then go back and do this. Because yes, that's exactly what we're doing.
Where do you get the, oh, never mind. It's in the same numbers from the top.
Say again?
The numbers are the same from the top.
Correct. We're still using f and g, which are defined in this question. So we would do the first arrow right there. This would be 2x cubed. 2x times x is 2x squared. 2x times negative 2 is negative 4x. Then we switch to the negative 1, which would give us negative x squared, negative x, and positive 2. After we double distribute here, we will combine like terms to clean it up, making sure we write it in the proper order. So we have 2x cubed plus 1x squared minus 5x plus 2. We took a function that was all real numbers and multiplied it by a function that was all real numbers and created a cubic function, which is still also all real numbers. So our domain has not changed again since we're combining unrestricted domains and making an unrestricted function type. But when you go to do the quotient, which tells me to put f on top of g, okay. So if we're doing f on top of g of x, here's what it would look like. We have f on top. We have g on bottom. We don't have to do any sort of cleaning up for this, just like boop, boop, put them on top and bottom. However, we've made a problem because now we have a denominator. And what are denominators not allowed to be? 0. So we're going to have to take this guy right here, this g of x function, and set it not equal to 0 to figure out the restrictions on our domain. So even though we took all real numbers divided by all real numbers, we now have a problem in that denominator. So we're going to take x squared, wrong color, x squared plus x minus 2, and we're going to say that cannot be equal to 0. We would factor and we would solve. What numbers multiply to negative 2 and add to positive 1? Let's make it positive 2 and negative 1, and then yes, which means that my solutions are not equal to negative 2 and not equal to 1. So even though we started with all real numbers and all real numbers, because we made a rational function, my domain is now from negative infinity to negative 2, from negative 2 to 1, and from 1 to infinity. We've created a problem by putting a function in the denominator. Here's where combining them with some of the simpler combinations would cause your domain to be different. So if we're looking at adding and subtracting maybe these particular functions, this time f is square root of x plus 3 and g is square root of x minus 2. Now your spidey senses should be going off because those are square root functions. So their insides have restrictions. Sorry, that should not be green, that should be blue. I'm the worst. So sorry. When I'm talking about the restrictions though, which is in green today, we're doing x plus 3 has to be greater than or equal to 0 for this first guy, and x minus 2 has to be greater than or equal to 0. Those were the rules from the front page when it came to square roots, which means for the f function, x has to be larger than negative 3 or equal to negative 3, and x has to be larger or equal to 2 for the g of x function. We keep that in mind, and we're going to combine these functions. It's asking me to do f plus g. When I do f plus g, all I'm going to do is take the f function, which is x plus 3, and I'm going to add the g function, which is square root of x minus 2. if you remember back to when we reviewed square roots in chapter 1, you cannot combine square roots together unless their index and radicand are the same. One of these says x plus 3, one of these says x minus 2. We actually can't combine this anymore. This is done. The problem is going to be determining the domain. So I'm going to go back to the idea we had from the whiteboards here. Oops, something didn't stick. And when we were on the whiteboards, wait for it. We had that one last question where we had to combine domains together. And I said it's easier to do this if you draw a number line. So if we draw a number line here, we have the numbers like here's -3. And here's 2. Okay. Our red function said that its domain has to be greater than or equal to -3. So the red function has this domain. Do you agree with me? Visually from -3 and larger. The blue function, however, has the domain of 2 or larger. The domains that I need to use is the intersection of these two domains. So where is this intersection? Where did both colors show up? From 2 to infinity. So the domain of this function is actually just going to be from 2 to infinity. Even though one of the other functions had a different domain, we have to use the overlap or the intersection of them to provide the most restrictive domain. From 2 to infinity. But again, if we're confused on what the domain should be, draw a number line. It will get a lot easier when it's a visual question than when numbers are just floating in the air. Function composition. So far today we have combined functions, and now we're going to compose them. This is a different way we can make functions interact with each other. So if you'll see, a composition of a function is denoted by f with, this is called a circ, and then a g, okay? This is not fog. Do not say fog. Oh my gosh, that bothers me so bad. This is pronounced f of g. It's telling us that we're going to have functions inside of other functions. So if you see f of g, what it's going to ask you to do is take the f function on the outside, and on the inside, you're going to tuck the g function in there. So you're putting functions in your functions. So beginning of class today, we worked on evaluating functions where you took a number, you plugged it into a function. Same concept, except we're taking functions, plugging them into functions. This makes our function machine have inputs and outputs. Those outputs become inputs, and then we get a second output. It's a double function machine.
Wait, so, can you say
So
that last part
we're
more?
putting, so we would have an input, we plug it into some function, we get an output. But that output immediately becomes a new input into another function to get a secondary output.
Okay, so you're doing it twice.
Yeah, it's like a chain reaction sort of situation. Okay? So before we start plugging in numbers, which is something you're going to be working on, we're going to be plugging in values and functions themselves. So if f is equal to 3x minus 4, which is a linear function, domain all real numbers, and g of x is x squared minus 2x plus 6, which is the quadratic, domain all real numbers. If we were doing what this first question says, which asks us to do f of g of x, we are going to rewrite it as f on the outside, g on the inside, because it reminds me which function goes on the inside. So I'm just going to copy paste the g function that was on the inside that set of parentheses. So it says f of, then I write the g function. Then I actually have to do the f function. So the f function for us says 3 times x minus 4, but the x is that function that we have plugged in. Based on what the math is telling me to do here, I'm going to have to distribute and then combine like terms. So I end up with f of g of x being the function 3x squared minus 6x plus 14. When it comes to finding the domain of a composite function, you look at the domain of the inside function and the domain of the final function. The inside function is a quadratic. Domain is all real numbers. The final function we wrote is a quadratic. Domain, all real numbers. So our domain of f of g is still all real numbers. Okay, Xander, ask your question.
Where did the x go?
For-
This is 3x minus 4, right?
3x minus 4? Correct, but x right now is this blue function. So we threw the x away, and in its place, we put the entire blue function,
And you put that in between?
wherever the x is.
Oh, okay.
If there's multiple x's, you'll put it in multiple places.
Okay. This is so sensitive.
Okay, let's try one together. Notice this one changed the order. This one says to do g of f of x. So this time, g is on the outside, f of x is on the inside. So we put g on the outside, and we're going to put the f of x function on the inside, just substituting in the expression for f of x. Now, I'm going to write the blue function, but everywhere there was an x, I'm putting the red function. So this equation would be x squared minus 2 times x plus 6. But everywhere there was an x, I'm putting the f function. Do we see what happened? You're putting functions in your functions.
So this one's just flipped from the other way.
It is. It's the opposite order. So instead of putting g into f, we're putting f into g.
And how would you know which one to do?
The order it's listed. So this one says f of g, g on the inside. G of f, f on the inside. After this, it's just arithmetic. It's telling me to square 3x minus 4, which if we double distribute, that would be 9x squared minus 24x plus 16. You might have to show some work to get there. You're double distributing or foiling. We're going to distribute the negative 2. This makes this negative 6x plus 8. And then we have our plus 6. Combining all of our like terms together, we end up with 9x squared minus 30x plus 30. And to do the domain of the composition, we look at the inside function. The inside function is linear, all real numbers. We look at the final function, that's a quadratic, all real numbers. So our domain is still negative infinity to infinity. Now this question changes how we attack it if it looks like question C. What is different about question C from question A and B?
There's a 1 instead of x.
There's a 1 instead of an x, which means if we are putting in a number, we should get out a number. Here's the math I want to see here. And I'm just going to do this all in one color because I feel like this is already color-coded a lot. We're going to do g of f of 1. We are working from the inside out, which means we need to evaluate the f function with a 1 plugged in. Do you see how I took the red function f, and instead of x, I put a 1? What is 3 times 1?
3.
Minus 4? So you said 3 minus 4, so that's negative 1. So now, again, if I'm working from the inside out, this just says g of negative 1. This is what we did at the beginning of class, right? G of negative 1 tells me to plug negative 1 into the g function, so I'm going to do that. Negative 1 squared minus 2 times negative 1 plus 6. Negative 1 squared is 1. Negative 2 times negative 1 is positive 2, and then drop down the 6. 1 plus 2 plus 6 is 9. So if you have a number that you're plugging in, you should get a number out. If it has an x you're plugging in, you should get an equation out.
So 9 is your answer.
9 is the answer. G of f of 1 is 9.
Can you plug in the g?
Can I plug in the g?
Oh, wait.
It says, because if we're working from the inside out, we would write this as g of f of 1. G of f of 1. So we go from the inside out. F of 1 says to take 1 and plug it into the f function. We do that. We get negative 1. This is saying take negative 1, plug it into the g function. Boom. So I have an input that becomes an output. That output I plug in as an input, I get an output. It's a chain reaction.
Oh, so that's where that.
Yes. Okay. I do want to re-emphasize because, again, most of the time your domain stays all real numbers unless you're using a particular function type. And I've said this a few times, but here it is written down. The domain of the composed function is the domain of the inside function and the domain of the final composed function. Those are the two you have to focus on. And that's going to be very important in this next problem. If we start this problem off, and we're going to compose these two functions, we'll have the f function 2 over x minus 1, and we'll have the g function of 3 over x. First things first, we think of the restrictions. For the red functions, x is not allowed to be the number 1, because 1 minus 1 is 0. What number is x not allowed to be in number 2?
3. Oh, wait.
What number would make that denominator 0?
0.
0. Okay. Now let's compose them, because we have our ideas of the domain of the original functions. It asks me to do f of g of x. And we're going to find the domain after we do this. Okay, well, I'm going to take then the g function, which for me is blue, and plug it into the f function. If I do that, anywhere there was an x in the f function, I'm going to put the g function. So instead of 2 over x minus 1, I put 3 over x minus 1. Sometimes you stop here. But I don't love the fact that there's a fraction in my fraction. So we're going to get rid of that fraction in the fraction by multiplying by the denominator of the fraction here. So what is the denominator of the denominator fraction? X. So we're going to multiply the top and the bottom by x. Like what's in the denominator of the blue function? X. We're multiplying everything by x, which means the top becomes 2x. The bottom becomes 3x over x minus x. Hopefully your spidey senses are tingling. 3x over x. Just 3, right? The x's are going to cancel. So my composed function written in a form that's acceptable is 2x over 3 minus x. This would be our composed function. Interesting. Our composed function is a rational function, which means we know that 3 minus x is not allowed to be equal to 0. What number is x not allowed to be? 3 minus what is equal to 0? 3. So x is not allowed to be the number 3. I need to create a domain for this composed functions out of two things. I need the restriction of the inside function, and I need the restriction of the composed functions. I'm combining them together. One of them says x is not allowed to be 0. The other says x is not allowed to be 3. So we combine those together to write the domain of the composed function that we can use every single number except for 0 and 3. So again, the inside function, which for us was blue, and the composed function, which for us was in the black there. I know there are questions. I would like for you to ask them when you're working at the whiteboards. So the last level today on the whiteboards, level 3, has 3 different types of questions. I would love for us to get through all of them. The third one is a challenge, but I think we can do it. Okay? Last time you were going to the whiteboards, we're done with notes for the day, so you can put the highlighters away. But you're doing level 3 at the whiteboards.